See you on the screen then?
Yeah.
Okay, perfect. Good evening, everybody. Morning for some folks in the US. It's great to see so much interest in these projects, and I'm very pleased to be able to present to you all today. So I'll be going through end-to-end deep learning deployment with the Open Neural Network Exchange. I'm Nick Pentreath. I'm a principal engineer at IBM, where I work in a team called the Center for Open Source Data. I focus on machine learning and AI. I'm an Apache Spark commit and PMC of that project. And I presented various conferences, meetups, and more recently a lot of more online events, obviously around the world on topics related to machine learning, AI, data science, and open source. We're a team of over 30 open source developers at IBM, and we work to support and contribute to and advocate for all the open source technologies that are foundational to IBM's AI offerings. So our aim is to improve the enterprise AI lifecycle in open source, and we do this by leveraging the Python data science stack. Apache Spark is a big part of that. Open source exchanges for both models and data sets, as well as AI fairness and ethics, Kubeflow for orchestration, and various open standards for model deployment. And that's what we'll be talking about today, is really the model deployment side of things. So we'll start with the machine learning workflow. And the typical machine learning workflow starts with data. We then analyze that data, and if we want to use it in a machine learning model, we typically need to do some form of pre-processing with it. Raw data doesn't just arrive in a format that is amenable to machine learning. It needs to be transformed into typically numerical vectors, tensors, before it can be fed into a model. So we need to do feature extraction, pre-processing, standardization, and all kinds of other transformations on that data. We then train a model, which is typically itself a sort of sub-workflow involving model tuning and selection, cross-validation, all the standard tools. And that's often in the past where the discussion about machine learning is stopped. But of course, a machine learning model is not useful unless it's actually deployed out into a real-world application. So we need to then deploy the model. And once it's deployed in a live environment, it is predicting on data, but we also have to maintain it and monitor it to ensure that it is keeps doing what it's supposed to be doing. We have to ensure performance is not degrading. We need to check whether it needs to be retrained and so on. And often machine learning models are generating new training data, or training data is arriving constantly. And that really turns this workflow into a loop. We go back to the data part of it. The workflow spans teams. Our data engineers are typically responsible for the data part of things, data storage, providing access in a scalable manner, access control, as well as creating things like feature stores and so on that can be used by the data science and research team. And they own this middle piece of the workflow, which is analyzing, processing, training. And once that you have a trained model, that typically becomes the domain of your machine learning and production engineers who are responsible for serving machine learning models at scale in a production environment. So this process has to span these teams, and they each have different objectives and in many ways different goals and needs. And it also spans tools, which is somewhat related to that point. There's a variety of data formats. Each data scientist, researcher, machine learning engineer has their own favorite language, framework, toolkits, and there's a wide variety of these. And in any team that's medium to large size, you're going to touch on almost all of these, and they all need to be supported at each phase in this pipeline. And finally, this whole process is just a small piece, but important one of the whole puzzle. So this is by now a fairly old image, but I still really like it because I think it's so true. And it comes from a Google paper, The Hidden Technical Debt in Machine Learning Systems, and it shows that the machine learning code, while critical and important, is really just a tiny piece. And it needs to interact with all the other different parts of the system. And in particular, what we'll be thinking about today is the serving infrastructure part of that. So if we think about machine learning deployment, what are we really talking about? What does it mean when we say that we're deploying a model? So we need to answer these three questions, which is what are we deploying, where are we deploying it, and how are we deploying? We're going to really talk about mostly the what today, but the other two questions are still obviously very important. So when we talk about a machine learning model, what do we really mean? Well, it's not just the trained model, which is an algorithm and a set of weights, but actually we need to incorporate the entire set of steps that come before that trained model. So as you mentioned, raw data doesn't just arrive in a nice format ready to use. We need to apply transformations, extract features, pre-process them before it can be used in a machine learning model. We then train that model in the training phase. Now, once the model is trained and deployed, when we predict in a live environment at prediction time, we need to apply exactly the same set of pre-processing steps. Otherwise, we effectively get a garbage in, garbage out scenario. If we don't apply exactly the same transformations, then the data arriving for our model prediction is different from what our model is trained on, and we get this training versus prediction time data skew, which is a serious problem and can, in some cases, result in catastrophic results, but in many cases may result in small errors that are very difficult to detect. We've all heard about deep learning obviously being very popular recently and making huge advances in all kinds of different fields. And one of the things that people often tell you about deep learning is that it doesn't actually need to do any feature engineering or data preprocessing, right? It bundles all of that in and it extracts features automatically, right? So this is what the deep learning pipeline looks like. You take an input image, you just throw it into your favorite huge deep neural network, and it gives you a prediction. But actually, in reality, deep learning has as much, if not more, need for pre-processing and careful thinking about what comes before the prediction as other models. So here is what even a simple image classification pipeline looks in reality. We still start, yes, with the input image, but we then need to do some pre-processing on that image. Typically, we decode it into a form that's amenable to the particular framework we're using. We're often going to be doing operations like resize, normalization, converting the types and the formats. And this is not done in necessarily a standardized way. Sometimes we're using a TensorFlow image module, Pillow, OpenCV. Each pipeline will have a different tool that's being used. Then when it comes to inference, of course, there's many different frameworks that can be used. And even after we have that inference result, we still need to apply some post-processing, which is typically mapping the predictions that come out, which are predicted probabilities for classes, and they are typically in a numerical vector or tensor format. We need to map them back and do some sorting to typically return, let's say, a top K predicted class. And this is often done in some sort of custom Python code, and it's typically not a standardized process. So if we dive a little bit deeper into this, we can see that even decoding the image can lead to some interesting challenges. So it may depend on the decoding library that's being used and different defaults between those different libraries and frameworks. It's quite easy in some cases to switch color modes on an image with some incorrect code, as well as the data layout. Each framework typically requires a slightly different data layout with respect to the height width channels, and that can be dependent on the framework. And it actually can be really tricky in some cases to know that a mistake has been made. So without diving into it and checking the images, a change in the color mode or the data layout can actually result in completely incorrect predictions. And these can be very, very subtle and very difficult to detect. And I've done this before myself. So I know from experience that it's not always obvious. And similarly, there can be different operation orders for things like normalization and type conversions. And depending on the order in which it's done, this can also have some small impact, sometimes large impact, but again, very subtle and difficult to actually realize what's going on. And then finally, inference post-processing requires a lot of custom Python code. So custom loading of assets and label mappings of vocabularies, custom code to decode the predictions and do sorting. So as you can see, there's a lot of custom stuff that is lying around in this pipeline. So really, we have to think about deploying not just the model, but the entire pipeline, the data transformations, feature extraction, of course, the model and algorithm itself, and even the post-prediction transformation. Technically, even our ETL phase is actually part of the pipeline because the model depends on all of that data lineage. And most frameworks don't take all of this into account. So we've seen many of the challenges, which I'll summarize here. We need to manage and bridge all these different languages, frameworks, dependencies, versions, and performance can vary a lot across these dimensions. So if a model is a Python model, for example, it's very difficult to know whether it's going to be performant in production. If it's pure Python code, or if it's inefficient code, it may not be very performant. But if it's wrapping TensorFlow, running on GPU, if it's wrapping NumPy and sklearn algorithms, for example, then it may very well be performant. So it's not always easy to know just by knowing what the language or framework is. Changes in versions can introduce performance regressions. So this can, each of these aspects that need to be managed introduce some variability. This is friction between teams, which we sort of hinted at before. Data scientists and researchers always want to use the latest and greatest. The production team does not like being woken up at 3 a.m. with a server on fire. They like things to be stable and under their control. And the business, to be honest, doesn't really care much about which framework is being used and whether your model is deployed on a Kubernetes cluster. They just care that the model does what it's supposed to do and achieves the business result. And of course, that it's always running and doesn't go down, impacting the business. Each framework does things differently in terms of the way that they represent models as well as pipelines and exported artifacts. And of course, for open source frameworks, you can go and have a look at those formats. For proprietary formats, you can't. There's lock-in and it's not portable at all. But even for the open source frameworks, they're not necessarily standardized. So you end up with a lot of custom solutions, custom code, custom extensions. So one solution that's often used these days in software deployment, and machine learning is no different, it's become very popular, is containers. So containers for machine learning should just solve our problems, right? We can just throw everything into a container and chuck it over the wall to our production team, yes? But in reality, it's not quite so simple. So container-based deployment does bring significant benefits. The most important, in my view, is the separation of concerns between the what and the how. So the data science and research team can focus on the what, what is actually going into that container? What is the model that they're building? What is the problem that they're solving? And they don't really have to worry as much about how it's getting deployed. That can be handled by the production team, who can take care of all the requirements for fault tolerance, high availability, and so on. And containers do give the separation of concerns. But still, what goes into that container is one of the most important factors. As we've seen, performance can be variable across all these different frameworks and languages and versions that need to be supported. So it does not solve this issue of standardization in two aspects: the formats that are used to represent what that model is, and the APIs exposed. And you still need some sort of serving framework on top, because you need a way for your application to read, to interact with that model. So this is where open standards come into play. So why do we need a standard? Well, as you've seen, if we have a standard format, we can export from all of these different frameworks that each do things in their own way to the standard format. So it provides the separation of concerns between the model producer and the model consumer. The model producer doesn't have to worry about where the model is going, how it's going to be deployed. All the model producer has. And really, it's the separation of concerns between the model producers and the model consumers. So the producers, which are typically the frameworks where you train the model, can export the model to a standardized format. They don't have to worry about where it's going to be deployed, how it's going to be deployed. And in a similar vein, the model consumer, which is the serving application and execution stack, doesn't have to worry about where the model was produced and where it came from. As long as it is represented in a valid standardized format, then that stack can then execute that model. It also allows for optimizing that single stack. So instead of having to support a whole plethora of different frameworks and versions and runtimes and optimize each and every one of them, you can focus on optimizing a single stack and have a single set of standardized tools for analysis, visualization, and so on. Now, we've heard a lot about open source and open standards today, so I think it's by now clear why all of this is important. But just to note that the open source license is obviously only one aspect. An open standard can be open source, but just because the particular project's format is out there in open doesn't mean that you have any control over that and how it evolves. So open governance is critical and helps to have visibility and transparency into development processes, strategic planning, roadmaps, and of course avoids concentration of control and gives more control to the entire community. Of course, there are downsides to having something within a foundation, or at least having everything standardized in an open standard. And the standard needs to have wide adoption and achieve this critical mass to succeed. So if it doesn't have that, and Ibrahim hinted at that before, you need projects that are used by many companies in order to drive adoption, and that interface with many other projects within the sort of data and AI plane. In some cases, a standard can move quite slowly, and you have a design by committee risk, and it can be a struggle to keep up with the pace of framework development. But really, overall, the benefits of an open standard and open governance far outweigh any of these risks in our view. So onto the Open Neural Network Exchange, or ONNX, which was established around 2017, originally by Facebook and Microsoft. It's a protocol buffer-based format for defining serialization of machine learning models. In particular, it was built originally for deep learning models. So it describes the computation graph, which is typically a directed acyclical graph, a common representation for deep learning and machine learning computation in general. And that defines a set of inputs, the operators that are applied to those inputs, and then the set of outputs. And it also encompasses the values or the weights within that graph. So in this way, the serialized graph is a fully self-contained artifact. And as long as you have a compliant ONNX protocol buffer, then you have everything you need to run that model baked into that. So it was focused on deep learning and tensor operations. So you can see that in a typical graph looks something like this. You have, for example, an operation, which is the green box, which is, let's say, matrix multiplication. It takes two inputs, which are these blue nodes, and performs the operation and specifies then an output. And if we translate that into this simplified example into an ONNX protocol buffer format, this is roughly what it looks like. So you have a top level structure, which is the graph, which contains a set of nodes, a set of inputs and outputs. And that graph represents the DAG, the directed acyclic graph. And each node specifies the inputs, the outputs, what the operator is. And then the inputs are specified, and outputs specify the types. Types typically being protobuf types, and typically these will be primitives and a tensor type, as well as some collections, which we'll see later. So here's an example of, let's say, a squeeze net, which is one particular neural network architecture. And this is using the Netron viewer, which has full support for ONNX. So you can plug in an ONNX model into Netron and view it in this format, seeing the inputs and all the different deep learning neural network operators. So ONNX supports all of the major deep learning frameworks. It actually was baked into PyTorch /Caffe2 version 1 as the interchange format. Still strong support there. There's good support for TensorFlow, and many folks in the community, including IBM Research, have been heavily involved in that. Keras, Apple, Core ML, MXNet, and many more. Now we've seen that the core deep learning support was really where ONNX started, and that's where support is definitely the strongest. But we've seen that pipelines, even in deep learning, really require some parts of traditional machine learning as well as pre-processing. So ONNX ML is the part of the spec, the ONNX spec, that provides support for these. So it adds a couple of types in addition to the sort of standard tensor type. And these are sequences and maps. And maps are very important, for example, in mapping integer code words or terms to integer codes for vocabularies, categorical and text feature pre-processing, and so on. It adds operators which are common in traditional machine learning, such as vectorization, encoding, categorical features, one-hot encoding, label encoding, scaling in the form of normalization, feature scaling, and so on, as well as your traditional models, such as linear models, tree ensembles, so random forests, decision trees, gradient boosting, and so on. ONNX ML has a wide community, an ecosystem of exporters that are written for the various traditional machine learning frameworks, including scikit-learn, where over 60 components are supported. LightGBM and XGBoost, your common gradient boosting tree-based libraries, which are very popular. Apache Spark has strong support, as well as Keras, LibSVM, Core ML. So on the right, we see an example of a LightGBM and sklearn pipeline where you actually have an sklearn component scaling the input in a LightGBM model coming after that. We can see that we can actually combine all of these different components. We can do feature pre-processing in scikit-learn and our feature engineering using that library. We can plug in a gradient boosting library or a deep learning framework at the end, and we can represent all of that in ONNX. So this is the role that ONNX is attempting to play in the ecosystem, to really be that standard that sits between the model model producers and the model consumers. So the ecosystem of converter libraries are taking the models from all these different frameworks into standardized ONNX spec. The ONNX model zoo is very active and growing all the time, and contains a set of widely used and state-of-the-art models across different domains, including image analysis, classification, segmentation, all the standard applications, natural language processing, translation, and various others. And those are all represented in ONNX formats across a couple of the ONNX operator versions, but they all should be kept up to date. And then when it comes to the execution stack, the ONNX runtime is an open source project by Microsoft, which is a fully compliant runtime supporting both the core set of deep learning type operators as well as ONNX ML. In terms of open governance, ONNX joined the LFAI Foundation at the end of last year. And as Ibrahim kind of intimated, there's a standard, fairly standardized governance structure with a high-level steering committee, very special interest groups that are focused on, for example, the model zoo and tutorials, the operator, the core operators, and specification within ONNX, converters, architecture, and so on, infrastructure, and so on. And then for specific new functionality, there are working groups. For example, at the moment, there's a training working group which is working on representing model, not just model export and inference in ONNX, but actually being able to train models within the ONNX spec. The other converter, the ecosystem of converter projects, as well as the ONNX runtime, are not yet part of the LFAI ecosystem, but some of them may well be in the future. Now, ONNX is still a relatively new project, and it's developing very rapidly. There's a monumental task really to keep operator and converter coverage up to date. So that's always going to be a challenge. For example, the TensorFlow project is huge in terms of scope, and it can be difficult to cover everything and to ensure everything's supported and up to date. Of course, the core, most important operators are there, but it's always going to be a challenge to keep up. Image processing, there is support for some basic image processing operators, but definitely some operators that would be nice to have the ability to read images directly, more advanced image processing. String processing, in particular, tokenization is not really supported very well, if at all, at the moment. Hashing, clustering models. So there's a few gaps. When it comes to exporters, for example, Spark ML supports only Python at the moment, which is generally okay because many users of Spark for data science will probably be using PySpark, but it does leave a gap on the JVM side if folks are using Scala, and makes it much more difficult to export into ONNX. And then finally, combining frameworks. We've seen that yes, you can use scikit-learn pipelines, then drop into TensorFlow, then drop into XGBoost. But at the moment, exporting a hybrid pipeline of that form is possible, but it's not necessarily that easy. One would have to export each piece and stitch it together yourself. So it requires a little bit of custom code. So, I think it's quite interesting to look at all of these. I call them missing pieces, but I think it's really exciting because they're great opportunities to potentially become involved if any of these are in the sweet spot of what your organization may be needing. And that's the beauty of an open source project, is that you can actually jump in to help out. So in summary, ONNX is a very active project, growing rapidly. It has strong support from large organizations, as well as small, including IBM and many others. It's highly performant. The ONNX runtime is very strong in terms of performance for inference. There's some support for traditional machine learning, and of course, LF Foundation AI, open governance. It's still relatively new. As I said, it's difficult to keep up with framework evolution. There's still a lot of work required, somewhat limited for image and text pre-processing in particular. But again, I think that ONNX will be moving in this direction, and there's always discussion around the roadmaps and the working groups with respect to converters and pipelines around these exact issues. And there's definitely a desire within the community to add these and to keep working on them. So to conclude, ONNX is an open standard for serialization and deployment of deep learning pipelines. It provides true portability across all of these different dimensions that we mentioned: languages, frameworks, runtimes, versions. It allows the separation of concerns between model producers and model consumers, and the optimization of a single stack. So in doing that, we believe it solves a significant pain point for the deployment of these deep learning pipelines in a fully open and portable manner. It's open source, open governance at ONNX.ai, so please get involved. Thank you very much. Really appreciate everyone joining, and appreciate you bearing with me in my power cut issues as I sit here in the pitch dark at home.